Okay, so sir has joined. Our chief guest today, Dr. Sandeep sir has joined.
You can make a co-host, sir. Manoj Kumar, sir. Manoj Kumar, sir.
Yes, sir. Yes, sir. I'm making.
Oh, okay, okay.
Okay, fine. Yes, sir. Everybody has joined so far.
Okay.
Mayuri ma'am, shall we start that, ma'am?
Sir, we'll just wait for some 2-3 minutes, sir. The participants are joining, sir.
Okay. Yes, sir.
Good afternoon, Dr. Sandeep.
Yeah, good afternoon, sir.
Good afternoon. I'm right. I think it's an afternoon. I think it's a
good morning
good
for
afternoon.
me. It's a good morning.
Morning. Good morning. Good morning. Good morning. So we used to have it's a quite different things. Thank you, sir. Thank you. And thank you for your accepting our invitation.
Yeah, thank you, sir, for invitation.
Probably we will start in 2 to 3 minutes, sir, actually.
Yeah.
Everything is ready. We will start in 2 to 3 minutes.
No problem, sir.
Sandeep sir, he's our Dean SCSC actually. From
Okay.
VIT.
Yeah.
Yeah, okay, sir.
Yeah.
Mayuri ma'am, shall we start, ma'am? Then students will be joining. It's not a problem.
Yes, sir. Okay, sir. Urvi and Ashwin, you can start.
All right, ma'am.
Am I audible? Hello.
Ma'am, Ashwin is actually starting with it. So could you please make him in the spotlight?
Already we have given him as a co-host. He can start.
Okay.
So am I audible, correct? Just to make everything clear.
Yes, you are audible, Ashwin.
Okay. So the astronomical growth of technology has impacted our daily lives in an unconventional way, which has made the world a much smaller place, and 2.3 million years just seems like yesterday. From the evolution of hunters using sticks and stones to hunt for prey to the relaxing comfort in our homes while we watch the food getting delivered to us in just 15 minutes. The transition from a Paleolithic era to the reigning era of artificial intelligence has embedded us into our everyday life is just a regular testament to the growth of technology.
Just learning the technical jargon has been a top challenge for many organizations. Deep learning is a good place to start. This branch of artificial intelligence has very quickly become transformative for healthcare, offering the ability to analyze data with a speed and precision never witnessed before.
Well, having said that, we welcome you all to our very insightful event, Deep Learning Frameworks for Clinical Diagnosis, a healthcare system organized by the very own AI division of VIT Bhopal with the sole aim of propelling young minds into the field of deep learning.
We are extremely privileged to have with us our Honorable Dean of School of Computer Science and Engineering, Dr. S. Poonkuntran sir, the Division Head of AI, Dr. S. Soundrajan sir, the AI Club Coordinator, Dr. AVR Mayuri ma'am, the Coordinator for today's event, Dr. Manoj Kumar sir from our AI Division, and our distinguished faculties from AI Division of VIT Bhopal. We are very excited to have our eminent speakers on board, and of course, the young and curious minds present with us in the audience.
We are very pumped up and excited to see such a large number of viewers who are connected with us. Having said that, I'd like to call our AI Club coordinator, Dr. AVR Mayuri ma'am, to address the gathering. Please, ma'am.
Good morning, everyone. It gives me immense pleasure to welcome you all for today's webinar on Deep Learning Framework for Clinical Diagnosis, e-Healthcare System. So we all know that deep learning is a part of machine learning, which is used to solve complex problems and also to build intelligent solutions. So the core concept of deep learning, it evolved from the structure and function of our human brain. So it uses the artificial neural networks to analyze the data and to make predictions. It is mainly widely used for the medical research, drug discovery, and diagnosis of life-threatening diseases such as cancer and diabetic retinopathy. So in today's session, our eminent speaker, Dr. Sandeep Singh Sengar, is here with us to tell us how deep learning has found its application in healthcare sector. I welcome you, sir, for today's event, and I am sure that all the participants of this event will gain useful insights from this session. Best wishes and thanks to all.
Thank you so much, ma'am, for setting such a high note with your kind words.
Now, I would like to take the privilege and honor to welcome our Dean of School of Computer Science and Engineering to spearhead this seminar with the inaugural address. Please, sir.
Yeah, thank you. Respected the guest for today's program, Dr. Sandeep from Cardiff School of Technologies, UK. Very warm good morning. And the organizing crew of this AI seminar, the AI division head and even coordinator, Professor Manoj, Dr. Soundararajan and Dr. Mayuri, and the student coordinator wing and all the participants, very warm. Good afternoon to every one of you. So I'm very happy to join with you all on this particular occasion. And today we all have gathered here to have a seminar on deep learning framework for clinical diagnosis coming under e-healthcare system. So if you could go back and if you could review our healthcare system. So if you see the evolution is started with the immobile healthcare system, but today it is accelerated with a lot of technologies and we are able to provide very good tech support in the healthcare. So the recent demand is increasing for a joint venture from engineering and to science with the medical science experts to provide a top-notch medical diagnosis tools under e-healthcare system. And we have also witnessed with the various types of e-health devices also in the recent times. So by this way, this particular seminar is today arranged to give you a comprehensive outlook of how this AI can be used in the healthcare. So I would like to register a few things. AI could be a common tool set today. The AI in healthcare and AI in finance, these are the two fields, and you can see a evergreen demand in these two fields. So by that way, I'm very happy to see today's seminar has been arranged in AI and healthcare. So with these few words, I wish you all the best, and I request all the participants to please interact with our speaker and get all the useful insights. I'm very sure, and our speaker is coming from UK. I know very well the Western countries are far away from Indian systems, where they have a very close interaction between the non-medical science people and medical science people. So they are having a lot of a pioneering system in bringing a lot of outcome in this e-healthcare area. So in this line, today our speaker is coming from UK, and definitely this particular interaction will be a very fruitful interaction. There is no doubt in that. So with this few words, I place once again my thanks to our speaker for being with us in today's seminar, and I wish you all the best. Thank you.
Thank you so much, sir, for your words of wisdom. We are moved by your kind and inspiring words. Now, we would like to welcome Dr. Manoj Kumar, sir, who is the faculty coordinator of this event, to introduce us to the eminent speaker. Please, sir.
Okay, thank you, Urvi. So, good afternoon, one and all present here. I am Manoj Kumar, coordinator of today's event. Take this opportunity to introduce today our guest, Dr. Sandeep Sengar, sir, who is basically from Uttar Pradesh, Hathras, and he is now currently working in computer science at Cardiff Metropolitan University, UK. Before joining this position, he worked as a postdoctoral research fellow at the machine learning section of the CSC department, University of Copenhagen, Denmark. He holds PhD degree from IIT Dhanbad and MTech in Information Security from NIT Allahabad. He has more than 7 years of experience in research and teaching. And if you talk about the research, he has done tremendous work so far in the research, having the interest in the medical image segmentation, motion segmentation, visual object tracking, object recognition, and video compression. The broader research contains about machine learning and deep learning. He's having the expertise in the computer vision, image and video processing and its wider applications. He has published several research articles in the reputed international journals and conferences in the field of computer vision and image processing. He is a reviewer of several reputed international transactions, journals and conferences, including IEEE transactions on system, man and cybernetics systems, pattern recognition, neural computing and applications, and neurocomputing. He has also served as a technical program committee member in many reputed international conferences. He has organized several special sessions worldwide, and he was invited as a keynote speaker in different conferences as well. So it's really a great day today because we are now celebrating this Durga Puja today and Gudi Parva. So I wish that this session is going to be a lot of brainstorming session for all my students of AI division and from other sections of SCSC and VIT Bhopal. Sir, I welcome to you in this platform to proceed the further session. Welcome you, sir, Dr. Sandeep, sir. Welcome.
Yeah, thank you, sir. Thank you. Fine. So shall I start?
Yes, sure.
Yes.
Please proceed.
Yeah. Okay. Okay. Thank you very much, each and everyone. And thanks for your nice introduction. And thanks for the invitations. I hope like you can see my slides, right?
Yes, sir.
Fine.
The slides are visible, sir. You may go ahead.
Yeah. Okay. Thank you very much. So first of all, good afternoon for all of you. It's a good morning for me, but like good afternoon for all Indian people. So once again, thank you very much for your invitation from VIT Bhopal. And today I'm going to present about the title Deep Learning Framework for Clinical Diagnosis e-Healthcare System. So in this talk, like we know, most of the people are currently working in machine learning and deep learning, right? And if we will ask from 10 people, then out of 10 people, 6 and 7 will tell, yeah, I have idea of machine learning, I have idea of deep learning, because it's a very active research domain or active topic nowadays. So the agenda of this talk is like, but some person might not be aware about this deep learning and machine learning. So I will give a little bit introduction of deep learning, then we'll move towards the research side of this medical imaging, medical application. So let's start with, the talk with my research area. I'm working in image video processing, computer vision, machine and deep learning. If anybody would like to work with me related to this area, then I will be more happy. I always have a habit to start my presentation with one beautiful picture. So there's a one picture, there's a one beautiful picture in front of you, and there's a one famous quote also. One picture is more than thousands of words. So that quote means like we can interpret many things from a single image, right? So there is an image in front of you. From this image, you can interpret the contents, like there's a small village, a small beautiful village, small like hill areas are there, they of green color, 2 tractors are there, different colors of skies are there. Likewise, you can interpret many things from this image. And who are interpreting? We are interpreting. Who we are the human being, right? If same task is done by the computer, means computer is going to interpret the content from image and video data set. Then it is called the computer vision, right? So I think you will not forget the definition of computer vision. Computer vision means just interpret the content of image and video data set from a particular, interpret the contents from the image and video data set, which is called the computer vision. Now, as this talk is based on deep learning, so let's learn about deep learning. What is the deep learning? So before deep learning definition, we should see this diagram. Here at the top, there is artificial intelligence. Artificial intelligence means machine is mimicking the behavior of human being, right? Machine is working just like a human being, just for example, robotics. And for example, like smart home concept. So then it comes to machine learning. Machine learning is a sub part of artificial intelligence. Machine learning means learning from previous experience, learning from the previous data set. And then deep learning. Deep learning is the subset or sub part of machine learning technique, which is the advanced version of artificial neural network. And artificial neural network is inspired from human brain and human neurons, right? Neurons are connected to each other. They pass information to each other in the same way in a deep learning or in the neural network. There are neurons. Neurons are connected to each other. They pass information to each other. And after that, they create the model. And once model is completed, we can predict the output. Now, specifically, if you're talking about the deep learning, then we should have a large data set for high performance, right? So in other terms, we can say deep learning is hungry for the data set. Now, some people talk about machine learning, some people talk about deep learning, like there is a little bit confusion. Both are independent, or what's the difference between both? So here you can see the difference. If you're talking for the machine learning techniques, then like we have an input image, we extract the features from the input image, means human being. And then we put those features in the classification model. It may be SPM, it may be neural network, and many other. And just we are going to find the output, whether it's a car or not car. So this is the way of deep learning, means we need to extract the feature, then we need to classify the data set. Now, next turn is for deep learning. In deep learning, just no need to extract the feature separately. Just give simple raw image as an input and generate the output. So our deep learning model takes care about everything. So that's why it is called the end-to-end approach, right? So this is the basic difference between both machine learning and deep learning techniques. Now there are different architectures of deep learning. So like some architectures are CNN, convolution neural network, recurrent neural network, long short-term memory, gated recurrent unit, deep leaf network, stacking network. So based on different applications, we use different architectures, right? So if you are talking for the image data set, or if you are, specifically we are talking for medical imaging data set, then mostly we need to apply the CNN, right? A convolution neural network. So this talk is based on medical imaging, right? We will use the e-healthcare system. E-healthcare system based on like medical data set, and this is a medical image data set. So we will apply the CNN, convolution neural network, on the basis on those application areas. Now we will learn a little bit, see the introduction of convolution neural network. So in just convolution neural network, just like a neural network, if you have idea of neural network, means like we have a more deep number of layers, more deep layers. So basic concept of CNN is like we have an input image, we assign weight, that's called importance. We assign weights to the input, like input image or input data set. Then we will generate the output. So in between, the target is to learn those weights. We need to learn those weights, right? So our output will come in an accurate manner, in a correct way. So this is the way we apply the CNN. We produce the output using CNN layer. Now, what is the architecture of CNN? There are different architectures. There are various architectures of CNN. So here we will discuss about one small architecture that's called LeanIt. So in LeanIt, like what is there? We have an input image, and there are different layers like a convolution layer, right? Max pooling, convolution, max pooling. So we can have many convolution, max pooling, many, like we have like 5 convolution max pooling, or 10 or 15 or 20, or maybe more than that also. So it depends on, completely depends on right problem, what kinds of problem we are going to solve. So basically there are 3 types of layers in CNN. One is the convolution layer, another is max pooling, and next is fully connected layer. If you're talking for the convolution layer, then convolution layer is used to extract the features, right? I think yes. So here, convolution layer is used to extract the features, right? And max pooling or pooling layer is used to reduce the complexity of our model. Reduce the complexity means just suppose we have a 1024 cross 1024 cross size image. If once we are applying max pooling of size 2 cross 2, then it will convert 1024 to 512, 512, means just half it will convert. So convert means it will reduce the complexity. Now, I will come back to this figure because here we are using some input image size, we are generating this output size. So I will explain you how we are doing all these, right? And here I've written max pooling, but it may be a min pooling, it may be average pooling, so depends on the problems. I will tell you all these points, how we are doing. Next, just learn about the convolution layer, how convolution layer works. So before the convolution layer, we need to understand the convolution operations, how convolution operation work. Suppose this is the input image, right? And we are just going to apply one filter, right, of 3 cross 3 size. Then what this convolution operation will do is element by element, it will multiply 0 to 4, 0 to 0, 0 to 0, 0 to 0, like that, right? And in last, it will add all these points. Whatever output will come, suppose -8 is coming, then this center pixel value will be replaced by that output. Now, this is the convolution layer, which like I have showed you in deep learning model, how this work actually in a CNN part. So just see here, we can see this is input image of size 5 cross 5, right? And we added one padding here. So this input image size became 7 to 7, 7 cross 7. And there are 3 channels. This is a color image. So this is a R channel, this is a G channel, this is a B channel, RGB. Now we need to apply the filter, right? So just whenever we apply the convolution layer, then this filter size should be same, just like an image size. Here there are 3 channels, 1, 2, 3. So in our filter also should be 3 channels, 1, 2, 3. And this may be vary. Like you can use 3 cross 3, you can use 5 cross 5, you can use 7 cross 7. It completely depends on you. So suppose in this case, we are using 3 cross 3. So what we can see here, I cannot annotate it. Okay. So what we can see here, like we need to apply this filter on this convolution layer. So what we will do, suppose you can see this dragging boxes are moving. So first, suppose assume our box is here at this point. Just see my cursor, box is here, right? And we are going to apply this particular filter on this box. The element by element we will multiply. 0 multiplied by -1, 0 multiplied by 0, 0 multiplied by 1. Same way, we will multiply all 9 terms, right? And we will add all these 9 terms. We will get the output here. Next, again, we will do the operation for this channel, right? And this filter. Same, we will multiply, we will add the answer here. Next, same way, we will do the operation for this channel. Now, in last, what we will do, we have 4 different values. One for this one, another for this one, next for this one, and bias. Now, we will add all these 4 values. Whatever output will come, that will be 2. So, we will keep this 2 here. Next, as we have taken stride value 2. Stride means how many times we are going to drag this box. So here you can see, if you see this clearly, carefully, then you will find like it is dragging this box. It is leaving one box, right? It is leaving one box in between. So that's why stride is 2, means it is crossing one. So S equal to 2. So next time, what we'll do? Next time, our box will come here. Then same operation we will apply, and we will add all these 4 terms. Then the answer will come 3. So right. So we need to repeat this step for W1 also. So for W0, this one will be the output, 3 cross 3. And for W1, this one will be the output, right? Now, there may be one question in your mind, why we are going to apply two filters here? Why not only one? Why not 3 or more than 3? Suppose this is the image. For example, you would like to detect horizontal edge in the image, and you also would like to detect the vertical edge in the image. So this first filter may be for horizontal edge in the image, and second for vertical edge in the image. So here we are going to detect the horizontal edge. Here we are going to detect the vertical edge. So it depends on the problem, what you want from your input data set. Based on that, you can assign the filters. Now, after applying the convolution layer, we need to apply different activation functions also, because we need to generalize the problem, right? So based on the problem, based on the requirement, there are different activation functions like sigmoid, tan hyperbolic, ReLU, leaky ReLU, max out, ELU. So you need to apply these activation functions to get the output. Here in the image also you can see convolution plus ReLU we apply, right? ReLU activation function we apply. Next, after that, we should go for pooling part. So here I'm going to explain the max pooling. Other pooling approaches also same. You will understand, I will tell you. So suppose we have an image size 4 cross 4, and we are applying the 4 cross 4 max pooling, then maximum value out of these 4 will come. So it is 9. Second, if you are taking 2 cross 2 max pooling, then what we will do? Just we will take this 2 cross 2 window. We'll take this 2 cross 2, and this 2 out of this 2 cross 2 window, we'll take the maximum value. So maximum is 5 here. So here maximum is 6. Here maximum 8. Here maximum is 9, like that. Now, if you are along overlapping between these 2 cross 2 maximum, so overlapping means just we have a stride one again, a stride one. So this is the window here. Then next time we will apply here. Next time we will apply here. So 3 cross 3 output will come. Right. So this is the this I talked for the max pooling. Max pooling is we are taking maximum value from 2 cross 2 window. There may be min pooling also, means we are taking only minimum value, or there may be average pooling also. But in majority of cases, we use the max pooling because we want the maximum value from our neighborhood side. Now, next layer is okay. So here, one more point I would like to tell you. If we are applying convolution layer, if our input image size is n cross n, suppose, and our filter size f cross n, then our output size will be n minus f plus 1, right? Our output will be n minus f plus 1. But if we are using stride and padding, then formula is little bit changed. That formula will be n minus f plus 2p divided by s plus 1. P is the padding, s is the stride. So just see here how these values are coming. Here, like input image size 32 cross 32. This is n equal to 32, right? F, in this case, f is 5 cross 5, means we are using 5 cross 5 filter. Then just we are using padding 0 and stride equal to 1. Then our output size will be n minus f plus 1. So 32, f is 5, 32 minus 5 is equal to 27 plus 1 equal to 28. So 28 cross 28 will be our output image size. And one more point here you need to consider, like if we have a number of filters 6, then our output size will be 6 cross 28 cross 28. Here also you can see, here number of filters are 2, 1, 2. So our output size will be 3 cross 3 cross 2, right? 1 and 2. So in the same way, if you have a number of filters 6, then it will be 6 cross 28 cross 28. Now, same formula for max pooling. I told you for max pooling. If you are using 2 cross 2 window, then this is the 4 cross 4. So out of these 4, only we are selecting 1. So for our final size will become 2 cross 2, means half of this one. If you are applying for 2 cross 2, no overlapping, then half of this one. So in the same way, you can see here how it is going. 28 cross 28 cross 6, then half of this is like 14 cross 6, right? In the same way, again, we are applying a convolution. So here 14 cross 6. So this is a convolution layer. So n minus f plus 1. So n is 14. F is 5, 14 minus 5, 9, plus 1, 10. And we are using 16 number of filters here. So 16 cross 10 cross 10. Same way, here max pooling again we are applying. So this will become half, but channel will not change. This number of filters will not change in case of max pooling. And in last, we are using flattening layer. So here you can see fully connected layer. Fully connected means all neurons are connected to each other and we are getting just output. Just same like a neural network we are going to apply. And in last, we apply either softmax activation function and sigmoid activation function in majority of cases. If this is a binary classification problem, right, see here, right? So if it's a binary classification problem, then we apply sigmoid activation function. If it is a multi-class classification problem, then we apply softmax activation function. So in here, the like input is car, and this is a multi-class classification problem like car, truck, van, bicycle, right? So we apply the softmax activation function. So actually this softmax activation function generates the probability. Probability means suppose in an input image this is a car, right? Then for car, there will be highest probability like 0.6 or 0.7. Then for truck, it will be 0.1, for van 0.01, like that. So we will move towards the highest probability. So according to highest probability, we'll tell in an input image, there is a car. So this is all about CNN architecture. Now CNN has been used a lot. People are using it in a very different way, and like they are getting very good results using CNN, which is a kind of deep learning architecture. Now, but in some application areas where we want precise information, very accurate information, right? Then in those areas, what happened, like whenever we are applying CNN, in that case, like we are not getting much accurate information, like medical imaging field, because if you are going to detect the cancer, right, the information should be very precise. Our answer should be very accurate. Otherwise, there will be lots of problems, right? So for that purpose, what happened, there is one more model came in 2015 that's called UNet model. UNet model is also a kind of CNN model, means convolution neural network model, means it's a variant of CNN model. Why it is called UNet? Because the shape of this model is just like a U, right? And same operations we are applying here, just like a CNN, like we are using this convolution layer, right? We are using max pooling, right? So this blue arrow represents the convolution layer. Here you can see the convolution 3x3 and ReLU activation function we are applying. Next, max pooling, then convolution, max pooling, like that. This left part is called the encoder, means the target of left part is used to extract the important features, right? Relevant features. The right part is nothing, just because here original image size is 572 cross 572. Then here we are getting only 32 cross 32, means we have reduced the image size a lot. Then we need to go for original image size back. So that's why it is just, we can say this is just reverse of max pooling. Just we are applying using this green arrow sign, right? And same convolution layer we are going to apply. Next, this is the bottleneck layer, means the connection between encoder and decoder. And here we are using skip connection, gray lines. So the target of skip connection is used to copy the features from input to output, right? Used to copy the features from input to output. So why we are going to copy the features from input to output? Because here we reduced the image size from 572 to 32, right? So it might be possible like we lost some important feature. So to recover those important features, directly we are taking data set from input. So this is called skip connections, right? And same convolution layer we are applying here. Just you can see 572 cross 572 image size, and we are using grayscale image because it's a 1. Now, once we will apply the 3 cross 3 filter on this one. So just remember the formula n minus f plus 1. N is 572, f is 3. So 572 minus 3, it is 569 plus 1. So 570, right? And we are using 64 number of filters here. So that's why it is 64. So final side will be 570 cross 570 cross 64. Same way, again, we are going to apply the convolution and we are getting this side. Next, we need to apply the max pooling. So max pooling will reduce the size into half. So 568 will make half will be 284. So 284 cross 284, and this filter size should be same, like 64. And again, we are applying with number of filters 128, and we are applying convolution, then 284 will become 282, right? So same things we need to repeat until this point. Then we need to apply up convolution here to make the size double, right? So this is the way we apply the unit, and majority of people are using unit for the medical imaging task. They are using for other application areas also, but for medical imaging areas, like it is perfect solution because it gives very precise information. And like it has been developed in 2015, just 7 years before, and it has lots of citations and other things. So like people are using this a lot. Now, just start with one of my work, medical imaging related work, in which like we applied these unit architectures. So the title of this work is Unit Architecture in Multiplanar Volumetric Segmentation, validated on 3D MRI cohorts. So here, what we had done, we have applied this unit architecture on 3D knee MRI image. Here you can see, like here, this is the 3D knee MRI image. On this, we are going to apply this unit architecture. But before applying this unit one, we are doing some operations, right? So this is the 3D image, and we are extracting slices, okay? We are extracting slices from different angles from this 3D image, or we can say from different coordinates. And this complete 3D image is called a scan, right? And extracted extracted 2D image called the slices in a medical term, right? So from this scan, we are going to extract the slices from different directions, because this 3D image, like if you can imagine the 3D image, then we can rotate the 3D image in many different directions. So for corresponding to each direction, we are getting like number of 2D scans. Now these 2D scans we are giving as an input in our unit model. So in place of unit, we used unit 2+. I will next slide, I will tell you the difference between unit and unit 2+. Then unit 2+ will generate, will divide it into the different classes. So this is the OAI dataset, OAI knee MRI dataset. This is a knee image. So there are 7 different classes in this dataset. So you can see 7 different colors. 7 different colors are there. So corresponding to each plane, this is called plane 1, plane 2, 3, 4, 5, 6. Like we have 6 planes here. So corresponding to each plane, we are generating the output, right? And we divided this plane according to the different axes, like sagittal axis, right? Transverse axis, like that. Now we are generating the output with different colors. Each color is representing the each class or each cartilage in the image. Now, one more point we can say, and this model, this block diagram is showing 6 planes, but we tested our model for 1 plane and 3 planes and 6 planes. And for 6 planes, it is giving the highest accuracy. That's why we are focusing on the 6 planes only. Now, next we generated 6 different output corresponding to 1 input 3D image. But we want output in 3D, right? These are the 2D slices output. We want output in 3D form. So what we will do, we will fuse this model, okay? We will fuse this all 6 different generated segmented result. And for fusion purpose also, we are using training, right? So each color is representing the weights probability, right? I told you in softmax function, we generate that probability. So each color is representing the different probability corresponding to each class. So we are using this probability as an input, right? And we are going to learn the weight. We are going to learn the weights using this probability. And in final, we are going to generate the 3D output corresponding to this whole segmented result. So same process we repeated for 3 planes, and same process we repeat for 1 plane. And for 1 plane, we extracted the 2D slices from sagittal axis only. Because from sagittal axis, we can extract the important information. So now, if you see this mathematical expression, then if we have an input size W cross H cross CH, then our output size will be W cross H cross K. Here, K is the number of classes. So in the case of this data set, there are 7. So K value will be 7 different colors. And here, what's the purpose of fusion? In fusion like this V is representing the number of planes. So in this case, 6. And K is the number of classes 7, so it will represent in the 7 form. So 7 dimensions. So like 7 different colors we are going to represent. Now, one more thing here we can see, like this output are generating corresponding to these each slices. And here, and one more thing, like you can see these slices from different angles, right? So of course, this output will also be from different angles. To make it this in this form, in a correct form, we applied the interpolation here. So nearest neighbor interpolation also applied for making it in a correct form, and we are generating the output. Now, here you can see like in what directions we are going to extract the planes. So this diagram is representing the directions. From different directions, we extracted the planes. And if you're talking for a particular direction, for single directions, then like suppose sagittal axis. So like this, we can extract the slices from this scan. And if you want to see the generalized version from all different directions, then you can see like from all different directions, we are going to extract the scans to apply the 2D unit architecture. And there may be one questions here, like why we are not going to apply unit 3D, because 3D unit is also available. Because 3D unit is like complex, like lots of computational power is required for that. So we want to reduce the complexity. That's why we converted this 3D into 2D, then we are applying on the 2D one. So in this way, like we work. And if you're talking about a fusion model, then like this is the input image. We are getting 6 different outputs, and we are going to fuse this model. We got this result, then we are going to compare this to true and predicted result. Now just if you have seen unit, and in this work, we focused on unit 2+, right? So just see the difference. In unit, just we have seen like encoder part, decoder part, skip connections, and bottleneck layer. In unit 2+, we have lots of skip connections, right? Skip connections means we have a medium coder also. This is encoder, decoder, medium coder. So in medium coder, we have lots of skip connections. They are connected to each other. Lots of skip connections we have. Right, and in output, we are generating this. So this is supervised model. Here we are getting this output from this place. So, right. So why we are using lots of connection in this one? Because we don't want to lose any information. Of course, the complexity of this model will be higher than this one, but we don't want to lose the information. That's why we can use unit 2+. And same way, there is one more architecture, unit 3+. In the literature, we have seen this unit 3+, but also claiming that we are also very good. We are performing better than unit. And they also claimed we are performing better than unit 2+. So we tested our approach for this architecture also. So here you can see the skip connection in a different way. Okay, right? So yeah, but in our case, the output of unit 2+ was very good. Means higher than others. That's why we consider only unit 2+. And now next we also compared unit 2+ deep supervised version and unit 3+ deep supervised version. So in unit 2+ deep supervised version, what we did, you can see in unit 2+ we are taking output from this point, but unit 2+ deep supervised version, we're taking output from this one, these 4 points, and we are applying some maximum like likelihood or right. and we are generating the final output based on these 4 points. And we also used unit 3 plus deep supervised version. So in unit 3 plus deep supervised version, we are using these 4, 1, 2, 3, 4. We are generating the output, and we are going to apply the maximum likelihood, and that will be the final output. But in our case, unit 2 plus was working great as compared to the all. So that's why we focused on this one. Now, this is the mathematical part that I already told you. We have an input size W cross H cross CH. We need to generate W cross H cross K. And here we are generating the segmented output. V means number of planes. So earlier we used 6 planes. So V value will vary from 1 to 6, 1, 2, 3, 4, 5, 6, right? And corresponding to each SP, we are generating this output, right? W, H, D, and K. So here you can see the output corresponding to output, right? This is a S1, S2, S3, S4, S5, S6, like that. So this is the way. And we applied the fusion also. For fusion purpose, I told you, we are using probability like PKXC. So PKXC is probability of class C at voxel X predicted by segmented SK, right? So if we are learning this probability, using the, like we are learning this weight using this probability. So probability will work like an input in our image, and this is a bias. So in 3D image, we call pixel as a voxel. I think you know, because there's 3 dimensions. Now bias and the weight. Okay, this is already told. Now see the experimental results. So we applied this model on 3 knee MRI data set, which are OAI, CCBR, and Lyra. For Lyra dataset, we collaborated with one of the hospital in Copenhagen, Denmark, and the radiologist provided this dataset directly. And this dataset is applied first time on our method. You cannot find this dataset publicly on internet, but OAI and CCBR are available in some literatures. But these datasets are also generated by the same hospital earlier. So these are very good and genuine benchmark data sets, and Lyra is private, and nowadays OAI and CCBR are public. In this data set, there are 60 scans in OAI, 140 in CCBR, and 39 scans in Lyra. Scans means 3D images. Out of those scans, number of slices, we are talking for number of slices, means number of 2D images from 3D. These are 9,600. And this is a 40,560 and 600 to 40. These are the scans, generated scans, right? Then if you're talking for the number of classes, then OAI, there are 7 classes, CCBR, there are 2, Lyra, there are 5 classes. Okay, so in the same way, there are other different parameters, scanners parameters. So radiologists use these parameters to extract the image. And this data set has been collected from Copenhagen people, right? They collected this data set from within like 4 years, 5 years, or 3 years. Okay, so Copenhagen people of different age groups. Okay, I'm not going much in the deep of this data set, but like from different age groups, they extracted this information, and we applied the method. And this radiologist validated our method also, results. So we calculated the DICE score for performance purpose, and that DICE score is compared. DICE score of our model MPUNet 2 plus is compared with existing model using pair t-test, right? Using Wilkinson rank sum test. So here, if the value of this pair t-test is less than 0.05, then we can say our alternative hypothesis will be true that we want for our model. And if it is greater than 0.05, then we can say our null hypothesis will be true. Means it is our model is not performing well. So to prove the effectiveness, our model should perform well than other. And in the other terms, we can say the alternative hypothesis should be true. And in other terms, we can say the value of this pair t-test should be less than 0.05. So in most of the cases, it is less than 0.05, except this one and this one. So we can say in majority of cases, our model is performing better than the other one. Now we also plotted this Boxer and Whisker plot for performance comparison purpose. And actually we want to generalize our model. Generalize our model means like we don't want to change the parameters if you are going from one data set to another data set. And we don't want any human intervention. Means whatever kinds of percentage coming, just give the input which you are going to generate the output without changing any parameters. So for that purpose, what we did, we combined all these data set, OAI, CCBR, and Lyra, right? We combined the dice score of all these data set corresponding to cartilage. Cartilage means classes. So here we are using only two cartilage, medial tibial and medial femoral. Why we are using only two cartilage? Because these two cartilage are available in all our three cohorts, three OAI, CCBR, and Lyra cohorts. So we combine the dice score corresponding to each cartilage, like medial tibial cartilage. We combine the dice score for MPUNet 2+, and medial femoral cartilage dice score we combine for MPUNet 2+. Same for MPUNet model we combine. Next, we plotted this Boxer and Whisker plot. So like if you want to see this Boxer Whisker plot, many of you might be aware about this, but I'm going to explain you. Like here, this orange line is representing the median, and this green triangle is representing the mean, and these are the outliers, and these are the different quartile, like 25, 50, 75, like that, right? Here, 25, 50, 75, like that. These are the different quartile. So if you want to compare this Boxer and Whisker plot, then you need to compare this first one to third one. Why? Because we are using medial tibial here, medial tibial here. Same cartilage we need to compare with different model. And you need to compare second one to fourth one, because medial femoral we are using, medial femoral we are using here. And you can see the number of outliers here. So our model is this one. This is a previously one. So here you can see there's a less number of outliers than this one. Here we can see there's a less number of outliers than this one. So in this way, we can say like our method is performing better than others in a generalized way for combining data set also. Next, we have seen this quantitative evaluation, but without qualitative evaluation, if we are not looking something from our eyes, then like it is hard to believe, right? So for that purpose, we have done qualitative evaluations also. So what we did, we compare the 2D slices. So this is the input image, right? Input image, we are generating the ground truth. This is the ground truth of input image. Then this is our method, and these are the already existing methods. So you can see like our method is generating the output close to the ground truth as compared to the other one. And one more point here, you can see like if you see this diagram, we cannot completely visualize the 3D image, right? Right? Miss, if you want to extract, if you want to visualize the total number of false positive or total number of error point, false negative, then it is very hard to visualize. So for that purpose, what we did, we have projected that 3D image onto 2D surface on the 2D plot. So this is the 2D representation of 3D image, complete 3D image. So what we are doing here, we are calculated total number of false positive from a particular cartilage, okay, from particular cartilage and particular cohort. And this false positive, we projected from 3D to 2D, right? So this is the 2D representation, two-dimensional representation of 3D diagram. And these colors are representing the total number of false positive. So we cannot see much difference, but in some slices, we can see, in some scans, we can see the difference. Right here, you can see in some data set, we can see the difference. Here you can see this is the MPUNet old method. So here you can see like this is the dark yellow kinds of things, dark yellow, dark green. Here it's a light green and light yellow. So here the yellow means we have a higher number of false positive, high number of false positive, right? So in this case, in our case, we have a low number of false positive. In the same way, we compared for false negative also, okay, for different cohorts for each cartilage. You can see like there are There are diagrams for each one, like for false positive, for false negative, and for each cohort and for each cartilage. So like we generated this diagram. Now, if you're talking for the conclusion part, then we applied full skip connection here because we don't want to lose the information. And this model has been applied for 1, 3, and 6 number of planes. And we have a total 30,400 number of scans from OAI CCBL LARA dataset. And this LARA dataset, which we have taken from hospital, right? And like it's a private dataset, and we have done extensive quantitative and qualitative evaluations using 3D and 2D. So this is all about the work. And now I would like to show you some more work. Like if some people, some students, or maybe some faculty would like to start work in medical imaging, and they are not getting idea how they can apply the deep learning and how they can apply deep learning and other techniques in a medical imaging field so they can generate good results. So I'm telling you some tricks using these works, already existing works, so they can start their research in a medical imaging area. So just think, after looking this block diagram, you will think how people are applying the different, applying the same techniques in a different way to get the good results. So like suppose this is the input image. And here we are applying some BGG19, means transfer learning. What is transfer learning? Means in some institutions and some organizations, like there's a lack of GPU support. They don't have a high power GPU, right? So what will happen, like they cannot run the model because this deep learning and other models require high computational like machine, like GPU, high power GPUs would be there. So we can apply this transfer learning in place of running the complete model, in place of like finding the complete model, just apply that transfer learning. So what is that? This is the already existing model. Just we can use the weights from existing model after changing the output layers. So based on this data set, we will just change the output layer and same weight we will use. So BGG19 here has been used. In BGG19, we have a 19 layers, 19 convolution and like max pooling or convolution max pooling and fully connected layers. Then we are applying ASPP. It is used for multi-resolution. That means from different resolutions, we are going to generate the features. Then there's a decoder part. Just keep in mind your unit architecture. So see the same architecture, and we are using skip connections, right? Then what they did, whatever output came, that output will go in the input of another unit one, right? And they will they will repeat this encoder part and the decoder part. There is a skip connection. They're like multi-resolution. They are getting output, and again they are going to concatenate this output 1 and output 2, and they're getting the result. So in this case, they improved the accuracy. Right? They are claiming this, these authors are claiming we improved the accuracy, and they perform this experiment on different types of data set, out of which one is the polyp data set, right? From Mackay challenge. So in this polyp data set, like this is a ground truth, this is generated from output 1, this is generated from output 2, right? And they also applied it for another data set, CBC Clinic TV. Right? So next you can see like different approaches, and they compare the result with unit. So it was like quite higher than the unit one. There was good amount of accuracy. In the same way, just see one more diagram, just see one more work that is called dense exception unit model. This architecture is also just like a unit model, right? This is same of this architecture, just like a unit model. Here, what we are doing, just we are taking input image and we are applying this inception residual block. In place of convolution and pooling layer, we are applying this block. So this inception residual block is also a very big architecture. I will tell you in the next slide. So we are applying different inception residual block, and we are applying different downsampling block and upsampling. In the decoder side, we are applying upsampling block and dense inception block we are going to apply. So we will see all these in a detail. So if you're talking about this inception residual block, so here you can see inception residual block. We have input image, different convolution layer we are going to apply, then a batch normalization layer we are going to apply, then we are generating the output, right? So here you can see in place of single convolution layer, we are applying many different operations in the sequence to get the accurate result. Next, you can see this dense inception block. So here you can see this is a dense inception block, this one. So dense inception block is also like very big, like we have an input, then another inception residual block we are applying, then batch like bottleneck layer we are applying, right? And then inception residual block, bottleneck, like we are going to repeat many times, and there skip connections also, and we are generating the output, right? And here we have one more inception residual block that we are going to apply here, input, and same, this architecture is same just like this one, but in place of, you can see 3x3 convolution, we are changed, like 3x3, we have used 1x3, because 1x3 means we want only the vertical image, like in a one dimension, one directions. Here 3x3, in the opposite direction we want 3x1. And in this case, we just use the same 3x3, 3x3, right? So this is the another part of this complete diagram. Next, we'll see the downsampling and upsampling block. Then in downsampling, we have an input layer. Then we are applying max pooling and other things, and upsampling opposite one. So here you can see the difference. In unit, just we applied a simple up convolution, max pooling, convolution layer, right? But here we are using this lots of operations. So just imagine if you will combine all these diagram in this one, in this single one, then how much complex it will be, right? Of course, the complexity is high and high GPU power is required, but this algorithm, this model gives good output, good accuracy. But in case of medical imaging, we need good accuracy. We should focus on good accuracy. We should not like focus on computational power much. So therefore, in that case, like it is very efficient architecture. So in this way also, you can think, you can design your model, you can design your architectures, okay? So for your research, and this has been applied on lung data set. So here you can see this is the label, this is the ground truth, and these are the results, right? So like the staging and validation accuracy has been tested. So these are the different results, training in terms of training and validation accuracy. Okay, so I'm not going for other topics because time is going up. Just we can see some we can see something like problems where machine learning, deep learning significantly suppress human labor performance. People are thinking why we are working for machine learning and deep learning, why we are focusing on machine learning and deep learning, why like human is not working. So there are some cases where machine learning like can perform better than human being. In those cases, human beings are not successful. For example, like online advertising. If you are advertising something, right, it will take lots of time, lots of human power, human manpower, right? So if you are doing online advertising using machine learning, then it's just amazing. Like you are, once you will open the Amazon site, right? Amazon site, and you will find some product, you will search some product, and suddenly you stop that Amazon site, you work somewhere else. Then on that site, you will get the advertisement related to that one, right? How it is coming? It is related to the machine learning, right? And product recommendation, same way, whatever I explained you, product recommendation, once you purchase something from the e-commerce site, then another product related to that will come in your internet, in your browser, right? So this product recommendation using machine learning, loan approval is automatic loan approval process. This is also complex in terms of human being, right? But if you're applying this online automatic, then it take like very low time and lots of data. If you have lots of data set, then deep learning, machine learning will perform in a better way. So these are the way. And like there are different application areas in which you can work other than medical imaging. So like object detection, object tracking, recognition, face recognition. Okay, I'm not going in a much deep of this one because we have less time. So like we can work, or you people can work on these application areas, and these are the latest one and very useful application areas nowadays. And of course, there are some difficulties, some challenges in the machine learning environment, in a deep learning, in a computer vision. Like it is difficult to simulate something as complex as human visual systems, right? Our eyes can see everything and they can analyze. But if you're talking to machine, if you're telling to machine, then it is will be difficult. And object may be in variety of size and ratio, right? Some objects are closer, then it will be big in size, far away, then small in size. So there may be problem related to that. Distinguishing one object from multiple others, variety of handwriting styles, curves, shapes employed while writing. And there are many other problems like deformation, appearance variation, scale variation, occlusion. So these are the challenges. But in spite of these challenges, people are working and they are working very well, right? And they are trying to improve this technology day by day. So this is all about the talks. Thank you very much. And thank you. So I'm going to stop. If any question is there, then welcome.
Thank you so much, sir. If the audience has any question, they may drop it down in the chat box. And Ashwin, you may take over.
Yeah, if you have any questions, guys, please do let us know in the chat box below.
Okay, I think we don't have any questions from audience side. So we can proceed for conclusion part.
Yeah, sure, sir.
So dear host, would like to conclude or should I do this one? Ashwin.
Yes, sir, I'm doing so. Like my mic was a little bit issue, so now I'm doing. Thank you, sir, for the great and enlightening session exposing us to the vivid field of deep learning in the healthcare domain. I'm sure a lot of people would go home right now and they would probably learn a lot more about it. Now, I would like to invite Dr. Manoj Kumar, sir, to deliver the concluding remarks. Please, sir.
Okay, so so finally we have reached up to conclusion side. So thank you very much, Dr. Sandeep, sir, for giving a lot of input onto the medical data and how deep learning models can be applied in a different form by doing a lot of adding on different layers and different max pooling filters and all these things. So basically this session was started from CNN and how it is being explored in some different kind of models. You have explained clearly and very well, and some mathematical well also. It was definitely going to be very much helpful for all the students who are having their interest in the biomedical field, and that how the all these deep learning models can be applied. And you have shown all three works very clearly, which is somehow a bit complex to understand a very first view. But yes, I mean, this is what actually we fail very first time with vision. So I mean, we are really very much impressed the way you have explained all the things very beautifully, though it is having a lot of mathematical computations. So I hope that everybody will take time and will go through all these things. And I would like to congratulate for all the successful of this your session. And from the Department of AI Division, I would like to thanks to Dr. Mayuri ma'am and Program Chair South Ranjan sir and Dean sir for believing me on me and giving me opportunity to conduct this webinar. And a special thanks to both to host Urvi Kashyap and Ashwin Ramesh Thank you very much, guys, for just a smooth conduction of this program. And every faculty member, I am really, really very much impressed that you people have shown your presence on this program. Thank you, everybody. Have a great day. Thank you very much, Sandeep sir. But before that, I wish you a very happy birthday from this VIT Bhopal.
Thank you very much.
Thank you, sir, for your presence, and happy birthday, sir.
Thank you, sir. Thank you.
Thank you, everybody. Thank you.
Bye.
Have a great day.
Many more happy returns of the day, sir.
Yeah, thank you, madam. Thank you.
It was so nice to have you over here on your birthday to our university.
Today is the birthday, and today my family is coming from India to London, so I need to go London after this talk. Okay. And like in between, I was looking in my phone, like college coming from my side, because they are on Delhi airport at present.
Okay.
So much for your valuable time with us, sir. Thank you.
Okay. Okay.
Have a great day, sir. Have a great day. Yeah. Thank you very much, everybody.
Bye. See you.
Thank you so much, sir. Guys, before you all leave the meeting, there would be a feedback form. We have to fill it so that you can get the attendance as well as the participation certificate for it. I'm pasting the link in the chat box, so everyone just check it out.
The link has been posted. As all good things come to an end, so must this. But as Sharon Begley once said, somewhere something incredible is waiting to be known. We would like to thank our speaker, our dean, our program chair, our event coordinator, and of course, all the people who helped us organize this event and turn it into a great success. Last but not the least, we would like to thank our lovely and energetic audience who had the patience and thirst for knowledge for attending the seminar. Where would we be without your enthusiasm, love, support that you all shower towards us? With this, your hosts, Ashwin and Urvi, are signing out. Thank you once again and have a blessed day.
Thank you everyone for attending this session. Please do make sure that you fill the form before leaving. Thank you all. Have a great day.
Thank you, Purvi and Ashwin. So it was very good. So let us wait for some 5 more minutes so that the audience can just take the feedback form and fill it. So all of you are requested to kindly fill the feedback form so that the participation certificates will be received to your email ID. Please do it. And thank you for attending the session.
Okay.